In this screencast, we're going to review for Exam 1. This is the first video, and I'll try to go over some of the more difficult concepts that we've covered. So I'm going to start with a problem I didn't assign, exercise 3.8. I thought it might be a little bit tricky to assign for homework. So the idea is to write a function to compute the greatest common divisor of two positive numbers using Euclid's ancient algorithm. So for example, enter the smaller number, 5. Enter the larger number, 15. Then the answer is 5. 5 is the greatest common divisor. All right, so let's look at the algorithm. Compute the remainder of dividing the larger number by the smaller number. Replace the larger number with the smaller number and the smaller number with the remainder. Repeat this process until the smaller number is 0. And the larger number at this point is the GCD. So I'm thinking we definitely need a while loop because we don't know how many times we'll have to repeat the procedure, so a for loop doesn't look like it would work. So let's try. So this is a model of our input and output here. So A equals, we make the type a little bigger. A equals int enter the smaller number. And we need the other number, B. Enter the larger number. Okay. So first thing we can do is do the division, but let's do that inside a loop. Now we may not get it right away. We may have to experiment a little bit to figure this out. This problem looks a little trickier than you might think. All right, so let's let C equal, so we have to compute the remainder of dividing the larger number by the smaller number. So C equals B modulo A. So that's the remainder. So for example, if we do 27 modulo 4, that's the remainder when you divide by 4. Okay, so C is the remainder of B divided by A. Replace the larger number with the smaller number and the smaller number with the remainder. Okay, so we have to replace B with A. So B is equal to A. And then replace the smaller number with the remainder. A equals C. Okay, we did that. Repeat the process until the smaller number is 0. And then the larger number is our answer. Okay, so let's see. So let's repeat this now inside the loop. While A is not equal to 0, why don't we just repeat these 3 steps inside the loop? So let's see. So we have our new A and B. B is the new larger, A is the new smaller. So we compute the remainder, B modulo A. And now we say B is now the old A is the old C. And it'll keep doing this until A is, as long as A is not 0. So when A is 0, it will stop. You could also say while A is greater than 0. That's also okay. And then when A finally is 0, the answer is B. So print the greatest common divisor. Let's put a is, and just to get a little practice, let's put a an integer formatted string here. And after the formatted string, remember we have to put that extra percent sign to say now we're going to be plugging in, and we simply put the variable here, which we said was B. Right? When A is 0, the larger number at this point is the GCD of A and B, and the smaller number is 0. All right, it looks good to me. So let's give it a try. Python. I call this program exam1 review a.py. Oh, I have a little error here. So I hope maybe you saw my error. So I forgot the word input. All right. Enter the smaller number 5, the larger number 15. All right, looks good. Let's try a more complicated example. 48. Whoops. I did them in the wrong order. So let's, but it looks like it gave the right answer anyway, right? Let's try a really big number. So as you can see, it's a pretty efficient algorithm that was able to do that so quickly. How about and the reason it's so fast is it's actually logarithmic. It really does decompose the numbers fast. In fact, why don't we see what's happening here? For some smaller numbers, of course, as an example. So let's print A and B, print A and B. Why don't we review something? So let's review our formatting output. So remember, you can use double quotes or single. The first is and the second is then we have to plug in and we put it as an ordered pair. Let's see. The first is and the second is A, comma B. And let's just copy this line. All right, let's see what it looks like. All right. So here's how Euclid's algorithm works. So 15 and 125. See, I think I made a mistake. See, I said smaller number, larger number. So it looks like it gives us the right answer, but it's not working out as nicely. So let's try it properly. So 15, 125. All right, so the first number is 5, and then 15, and then 0, 5. In fact, let's put one more of these in, just so that we could have it line up nicely before we change anything. Smaller number, 15, 85. All right, see how it lines up so nicely? Okay. Our next exercise will be to find all the prime numbers up to a certain amount. So let me comment this out. So if you have a nice editor, you can uncomment an entire block of code in one shot. And in fact, you can comment it and uncomment it, see? And what's even pretty neat, I didn't mention this in class, but I probably should. Let's say you wanted to put this inside a loop. You can shift the whole thing right, see? And then you can shift it back left. So this is how you can cut and paste blocks of code, because you do have to indent properly. All right, so let me comment this out again. Okay. By the way, this is called BB Edit. It's a free program, and it's really, really good. It works only on Mac, but there are other programs that you could use on Windows. But this is a nice program in particular. Okay, so let's write a program to find all prime numbers up to a inputted number n. All right, so let's copy some code from here. All right, so let's see, n, enter a number. All right, so we want to check if it's prime, and we want to find all the numbers up to n and see if they're prime. Now this is not going to be very efficient. When we learn arrays, we will be able to make it more efficient. All right, so for I in range 1 to n plus 1. Right, we're going to test every number. Actually, we don't need to test 1. We know 1 is not a prime. 2 is the first prime. So we can do that as a special case. So if I equals 2, print the number D is prime, and we'll plug in I. All right, so that's our special case. Else, so it's not the number 2, we have to do some calculating, right? All right, so how do we know if a number is prime? Well, we must check all the numbers less than that number, whether they divide into it. And we actually only have to go up to the square root. Once we get to the square root of the number, we don't have to divide, we don't have to check anything greater than the square root. So let's see. So let's let n, let's let j equal, we need the square root, right? So we need to import the math library. So let's import the math library. So import math. Okay. This program might be a bit longer, so I won't put any extra spaces in. All right, so j equals math dot square root of, so we're looking at I. I is the number we're thinking of. Square root of I. But then we want to take the integer of that. This is just a math thing. Plus 1. What I'm saying is this number j is the biggest number we need to check to determine whether I is a prime number. The math is simple, and you can skip the math if it bothers you. We're just doing the programming exercise anyway. All right, so j, this is what we're going to check. So now we need to divide every number up to j and including j into I and see whether any of them have a remainder that's equal to 0, to see if any number goes into I. So let's see. So let's start out by saying prime equals false. Let's assume prime is a Boolean variable and it's currently false. So for well, okay. So for k in range, so we're going to divide 2 from 2 up to, say, j plus 1. And we're going to check I divided by k, take the remainder, so I modulo k, is this equal to 0? So this is a Boolean variable. This is a Boolean expression. So if that is true, then prime is going to equal the value of that Boolean expression. So if we do find a number k that divides into I, then it's no longer prime, right? So then it's not a prime. So maybe our logic is reversed. So perhaps this should be true. Let's assume the number is prime. And if we find a number that divides evenly into I, then it's definitely not prime, right? Then it would not be prime. So, you know what, maybe I'm making it a little complicated this way. Let me show you another way to do this. That probably is a little easier to understand. So if I divided by k is equal to 0, then I is not a prime number, right? So prime equals false. So if we wanted to do it this way, instead of with an if, we could say not. So prime equals I modulo k is 0. So the remainder is 0. So that would be true. So we're saying not that. So, but this is actually a bit confusing. So I believe it's correct, but I'm going to delete it because this is a lot easier to read. So if I divides k evenly, then it's not a prime number, right? So we figured out that I is not a prime number, so we can go on to the next number, correct? So what we would end up doing is we would break out of here. So this break is a way to break out of the current loop. So it'll break out of the loop, and it'll break out of this loop, and then we'll go back to here and go on to the next value of I. So let's say we go through the entire range, right? And none of the numbers divide. In that case, prime is true, right? We never change prime. So we are done with the range. We're done with this loop. And we could say if prime, remember it's a Boolean variable, print out that this number is prime. By the way, it might be easier to write a program to first check if a single number is prime, and then copy that code into a loop. I didn't do that here, so it might be a little more difficult to follow, but you might want to try that. All right, let's see if it works. Let's see if we made any mistakes. Let's say 15. All right, it looks like our logic is sound, right? Only thing that I don't like is it's not lining up nicely, right? We could fix that with a 6 here. Let's try, just in case we have more digits, 10 there. So now we're reserving a field width of 10 for that unknown number there. Okay, that looks good. Let's try some bigger numbers. All right, those are the numbers up to 10,000, the first primes. And how many numbers are there? $100,000? How many numbers are there? What percentage of the numbers are prime? That's a famous math theorem called the prime number theorem. We can easily check this. So percent equals, well, we need to keep track of how many are prime, right? So let's see. We need a variable. Num prime equals 0. So if this, every time we print, we found a prime, right? So num prime plus equals 1. And we found a prime here. So num prime plus equals 1. So percent would be num prime divided by n. So I did verify that when you use the division, the single division, it does automatically convert things to decimal. I mean, I personally would do something like this just to be safe, because other languages aren't so nice. But if you do with the double one, that's the integer division, that's the quotient. But if you just do one, that's actually the decimal division. So it is safe to do that. But just to be sure, you could say float num prime divided by, float. We could convert it to a, whoops, sorry about that, float. As you can see, I'm a math person and not a great speller. All right, so that's our percent. And then let's print percent prime So let's use 5 decimals of precision, and with our printing. And then let's plug in percent. All right, so let's see. Okay, exit out of the interpreter. All right, so the number of primes is 25% are primes. Let's try a bigger number. See, it slows down by having to print. If we took away this print, you would see it would be a lot faster. So let me show you. So put a number sign there, number sign there, save it. It's still going. Control C interrupts. .07850. And if you want to know what that number is, it's x divided by the natural log of x. So that's how you